Welcome back to The Explainer. So, you know that feeling when you're standing in complete darkness, maybe in a pitch black room or out camping in the woods, and you feel like your eyes are just totally playing tricks on you? Well, today we're going on a really fascinating biological journey into exactly how our eyes and our brain process darkness. It's this incredible story of evolutionary survival, rapid physiological transformation, and honestly, what happens when our mind is left all alone in the dark.
And this brings us to a slightly eerie yet deeply relatable question. Why do we hallucinate in the dark? I mean, have you ever stared into the shadows and sworn you saw something move? Or maybe you've noticed a faint, kind of shifting pattern of geometric colors where there should literally be nothing but black? To solve this central mystery, we need to understand two things: the biological hardware of our eyes and the computational software of our brain. All right, section one, the dark vision mystery. Let's look at low light environments.
Moving right along to section 2, switching cones to rods and the duplicity theory.
To understand how we see in the dark, we first need to look at the massive evolutionary challenge of low light environments. When the lights go out, your eyes have to perform this rapid biological handoff. See, during the day, you rely on your photopic system. That's driven by about 7 million cone cells clustered right at the center of your retina in an area called the fovea. Cones give you high acuity, full color vision, but drop below a certain light level, and those cones become completely useless. That's when your scotopic, or night vision system, takes over. This system uses 120 million rod cells spread across the periphery of your retina. Rods don't see color at all, which, by the way, is exactly why night vision is in shades of gray. But they are exquisitely sensitive to even single photons of light.
So, imagine you step into a dark room. For the first 10 minutes, your cones are desperately trying to adapt, but they hit their limit pretty quickly. Right around that 7 to 10 minute mark, you hit what's called the rod cone break. This is the critical inflection point where your rod cells finally surpass your cone cells in sensitivity and take over the heavy lifting. And by 30 to 120 minutes in, your rods have reached their absolute maximum potential. And the result of this transition is staggering. Once your eyes are fully dark adapted, and this visual pigment called rhodopsin is completely regenerated in your rods, your eye becomes 10,000 to 1 million times more sensitive to light than it is during the day. I mean, that is just an absolute masterclass in biological engineering.
Section 3, blind spots and color. Let's get into optical illusions. Now, relying entirely on scotic vision means our eyes have to sacrifice sharpness for sensitivity. And here is where it gets weird. Looking directly at a dim object at night makes it literally disappear, because the absolute center of your vision, that fovea we talked about, is packed exclusively with daytime cones and is completely rod-free. You actually develop a temporary night blind spot exactly where you usually focus your eyes.
That rod-free night blind spot is about 5 to 10 degrees wide. If you stare directly at a dim object for more than 2 seconds, it falls right into that cone-only zone and just vanishes. Poof! This is actually a huge deal for pilots trying to spot other aircraft at night or astronomers looking at dim stars. The practical workaround for this is a technique called averted vision, which basically just means looking slightly off to the side, shifting the incoming light onto the rod-dense periphery of your retina. Alongside that blind spot, darkness fundamentally distorts how we perceive color. This is known as the Purkinje effect. It's an optical phenomenon first noted way back in 1819 by the Czech anatomist Jan Evangelista Purkinje during dawn walks in blossomed fields. It happens during the twilight, or mesobic state, when both your rods and cones are pooling their signals together.
And this brilliantly illustrates the Purkinje shift in action. In daylight, our eyes are most sensitive to greenish-yellow light. But as darkness falls and rods take over, our peak sensitivity shifts toward the greenish-blue wavelength, right at 507 nanometers. The result? Red objects suddenly appear extremely dark, or even pitch black, while blues and greens pop out and appear unusually bright. It completely distorts your color contrast and even messes with your judgment of distance. Okay, part 4, the predictive brain. Moving into top-down processing.
Now that we understand the bottom-up hardware of the eye, the rods, the fovea, the pigment shifts, we need to move up the chain and look at the top-down software of the visual cortex. I love this quote because it gets right to the heart of modern neuroscience. Your brain is a prediction engine, not a fancy camera. For the longest time, we thought of perception like a camera. Light goes in, the brain processes it, and boom, you see a picture. But neuroscientists like Carl Friston have totally shattered this with the neurocomputational model of predictive processing. Your brain is actually a highly active prediction engine. It is guessing what's out there before you even see it.
Think of it like this. Your cortex constantly generates priors. These are top-down predictions based on your past experiences. It sends these guesses down the visual network to meet the bottom-up sense data coming from your retina. If they match, great. If they don't, your retina sends back a prediction error. And to save incredible amounts of neural bandwidth, your brain actually only brings these prediction errors into your conscious awareness. But what happens in the dark? Your rod cells are highly sensitive, sure, but the visual data they send up is degraded. It's blurry, it's colorless. Faced with this low-quality sensory input, your brain cannot tolerate a perceptual vacuum. It hates it. So it's forced to aggressively rely on its top-down priors. It literally just has to guess what you're looking at.
And finally, Section 5, the Ganzfeld effect, total sensory deprivation.
When you combine a brain desperate for input with an environment providing absolutely none, you enter the wild realm of sensory deprivation. Psychologist Wolfgang Metziger introduced this concept in 1930. The Ganzfeld effect, which comes from the German word for complete field, is what happens to your perception when you are exposed to a completely unstructured, uniform field of vision. It could be an entirely pitch-black room or even a completely featureless white Arctic landscape.
So here is the step-by-step chain reaction of how this works. First, your visual field goes completely dark or uniform. Second, your brain becomes starved of structured bottom-up input. Third, trying desperately to find a signal, the brain cranks up its internal gain and ends up amplifying its own baseline neural noise. And finally, your prediction engine misinterprets that internal static as external reality. Your priors override your senses, creating full-blown hallucinations.
This feedback loop really reveals the incredible power of the mind. This amplified neural noise creates what trapped miners actually call the prisoner's cinema, flashes of color and geometric patterns in pitch-black caves. It's exactly why Arctic explorers staring at featureless snow for days report vivid, complex scenes out of nowhere. Your brain misidentifies its own internal noise as reality, literally projecting a movie onto the blank canvas of the dark just to keep itself occupied.
So the next time the lights go out and you see a shadow move in the corner of your eye, just remember, it's probably just your 120 million rods and your overactive prediction engine trying to keep you safe. Bell, subscribe for more fast-paced, mind-blowing science videos. Comments, what's the creepiest thing your eyes have ever faked in the dark? Let us know in the comments below. #ScienceFacts, #biology, #neuroscience, how we see, human body, the fact lady, optics, survival instinct.